Mapping electric field lines. As background material, please review electric field lines and equipotential surfaces that can be found in your textbook or in OpenStax. Let's summarize some of the features of electric field lines as it relates to equipotential surfaces. With a positive plate shown on the left and a negatively charged plate on the right, the electric field lines, indicated as red arrows, is essentially represents the direction of electric force that would be felt by a positive object. So I'm showing a smiley face there. Wherever the smiley face is placed, if you pretend it's positive, it would want to repel from the positive plate and attract to the negative plate. And therefore, in this kind of geometry shown, the smiley face would always feel a force to the right. So our electric field line pattern is a pattern of arrows that goes from left to right. Now, if the smiley face was removed, it's still nice to think in terms of source charge, the actual plates, that electric field goes from positive charge and or to negative charge. Electric field also goes from high to low volts. So as we travel with the electric field, in this case to the right, we would be traveling to lower volts. If we go against the electric field to the left, we're going to high volts. So to travel in such a way that we don't change the volts, we'd have to travel perpendicular to the electric field lines. And that dotted line indicates a surface cutting into the screen that represents what's called an equipotential surface. Now also, electric field lines are perpendicular to conducting surfaces, and electric field lines are always perpendicular to equipotential surfaces. Also, the density of electric field lines indicates the strength. Where the lines are close, it indicates a strong field. Where they're more spread out, a weaker field. So in order to discover electric field lines, we can actually use a voltmeter to first discover the equipotential surfaces. So here is a grid and some hypothetical electric field lines shown in red that we don't know where they came from, but they're there. With a voltmeter, we can, for example, take the black probe and set it somewhere, right? We'll pick a point. Call that a set point. Then as we move the red probe around, the voltmeter measures potential difference, or volts, across the black to red probe. So in this case, I have 8.5 volts, and that means the red probe tip is 8.5 volts higher than the black probe tip, right? So that means the red probe did not find a point that is on the same equipotential as the black probe, right? So when we do this, we'll move the red probe around systematically until we find 0 volts. And once we find 0 volts, then we know the point that is where the red probe is located, the tip of the probe. We'll know that that point is part of the equipotential that includes the tip of the black probe. So here is the actual setup that we'll use. There is a grid that goes from -4 to +4 units on X and on Y. The actual units are not important, whether it's centimeters or inches, so we'll just call them units. A positive charge is at -4, 0, and an equal negative charge at 4, 0. So because the positive charge is on the left and negative charge on the right, we roughly expect the electric field to go from left to right, but not uniform because these are point charges. But that's how we'll determine how to move the probes, right? So if we set the black probe tip at various points, in this case shown, the first one shown here is -3, -3, then as we move the red probe horizontally from left to right, we should be going down in volts. and we'll be able to find the point where the volts goes to zero, or as close to zero as possible. What is shown here is the voltmeter showing a positive 8.46 volts. And again, that means that the red probe has not found a point that belongs to the same family of points that was set by the black probe, right? So we need to find 0 volts first with the red probe to get the coordinates to go in the little table that you see on the right. So we are going to seek 5 equipotential lines, and each line will be represented by 7 points, one of them set by the black probe, the other 6 being discovered by the red probe. What follows now will be an animation that lets you collect data. For each set point, you'll see a table that shows the set point first and 6 more points, so a total of 7 points per equipotential curve. Right, so you may have to pause or slow down the playback to catch the coordinates that show you a 0 volt reading or as close to it as possible so that you can fill in the missing cells in each of those data tables. And now on to the data analysis. We have 5 sets of points. Each set of points represents an equipotential line or curve, and each set has 7 points. First point set by the black probe, the other 6 discovered with the red probe. If you graph those sets of points, you will be able to visualize the equipotential curves or lines. The assignment details will be posted.